Okay, in this lesson I want to look at Newton's laws and connected particles, but using those, what we've learned already, but together with our master equations of kinematics, our uvast equations. Remember, one thing that's important about the master equations is they all rely on A being constant. If A is not constant, then those master equations of kinematics are useless. So they're all based on a constant A. So let's look at this question here. We have a system with a 10 kg, 4 kg. I haven't written it in, but you can assume that the pulley is smooth, the string is light and inextensible, no friction, the string is of negligible mass. That's the kind of system we're going to look at. As we release this, it's fairly obvious what's going to happen. I release it from rest. 10 kilogram will outweigh the 4 kilogram. So 10 kilogram will go down, the 4 kilogram will go up. I want to investigate how fast it will be traveling when it has traveled 2 meters. How fast will it be traveling when it has traveled 2 meters? In terms of, my notation, what they're asking me is to find the velocity when the displacement is 2. That's what I'm being asked. One thing I know is I can calculate the acceleration of this system. Okay, so what am I going to do to calculate the acceleration of this system? Well, I'm going to use force diagrams to I'm going to use some force diagrams to help me calculate this out. One thing I will mention that I already know, that the acceleration of this system will be 6 over 14 times g, or 3/7 g, or 3g over 7 if you prefer. I know that. How do I know that? Well, based on stuff I've looked at in previous lessons. So I know that this will be 3/7 g, the acceleration of this thing. I'm going to go through the steps though in order to find it. I'm going to start with force diagrams. I'm going to draw a force diagram for my 10 kilogram particle. I'm going to draw a separate force diagram for my 4 kilogram particle. From my force diagrams, I'm going to come up with a couple of force equations based on Newton's second law, F net equals ma. That'll give me 2 equations. And from those equations, I'm going to solve the system finding values for the variables that satisfy both equations simultaneously. So force diagrams, let's start with those. For the 10 kilogram mass, again, the picture doesn't have to be perfect. The first force at work on the mass is the force on the mass by gravity. That's called the weight of the object, which is always mass times little g. In this case, it'll be 10g. The other force acting on that particle is the force on the particle by the string here, pulling upwards. That force is called the tension force. Looking at the 4 kilogram particle, the force on the 4 kilogram particle by gravity, that's called the weight, which is always mass times little g. And then the force on the particle by the string, which is called the tension. I'm going to think about the direction of these things, and it should be fairly obvious that the 10 kilogram mass is going to travel downwards and the 4 kilogram mass is going to travel upwards, and both of them accelerating. The 10 kilogram mass accelerating downwards, 4 kilogram mass accelerating upwards. Because this is going to accelerate downwards, I'm going to call it a down positive system. Because 4 kilograms is going to accelerate upwards, I'm going to call it an up positive system. That's what I'm going to do, and I'm going to figure out my equations based on these things. Okay, looking at the first equation, F net, remember it's a down positive system, so my 10g is a positive force, my T is a negative force, so my net force for this first system is going to be 10g subtract T. 10g is positive, T is a negative force. That's equal to the mass times the acceleration. The mass is 10, the acceleration is A. We have to figure out what that is. In the second case, up positive system, which means T is positive, 4g is negative. So my net force will be T subtract 4g, and that's going to equal to mass 4 times the acceleration, which we don't know. Adding those two equations, using the addition property of equations, adding the left hand sides, 10g added to negative 4g, that's 6g. T added to negative t, the t's will cancel here. 10a added to 4a on the right hand side, that's going to be 14a. And solving for a, dividing on both sides there by 14. We'll find that a is going to equal to, well, 6 over 14 times g, which simplifies to 3/7 g, which, if you remember, I said right at the start, that's what it was going to be, because, you know, I know something about systems of this type that allows me to find the acceleration quickly. I went through it in my last video lesson. Okay, but I don't need to know that piece of information. I can always use force diagrams and then the force equation to find the acceleration. Notice the acceleration here is a constant. So that 3/7 g is a constant, not a constant, a constant. So a is a constant, 3/7 g is a constant, g is a constant value. So the acceleration is constant. Therefore, you know, what am I trying to find? V when s is 2. If the equation is, if the acceleration is constant, I can use my master equations, and we know from my master equations that v squared equals u squared plus 2 times a times s. Notice the system's released from rest, so u will be equal to 0. So solving there, I'm going to get v squared is equal to 0 squared plus 2 times a, which we said was 3/7 of g, times s. Well, s is given here as 2. So I'm going to get v squared is equal to, multiplying everything out, 2 by 3, 6 by 2 is 12. That's going to be 12g over 7. Okay, that's giving me v squared. Remember, what I'm actually trying to find is v, the velocity of the object. So v is equal to the square root of all that. That can go straight into your calculator. So just dig out your calculator, type in the square root of 12g over 7. Maybe it works out nicely, maybe it doesn't. You dig g here to be 9.8. So I'm getting 2 root 105 over 5, and that's meters per second. Okay. If I wanted to approximate that, that's about, excuse me, I'm going to put my approximately equal sign pointing up here, you know, just to preserve space. That's about 4.1 meters per second. So when the two objects have traveled, 10 kilogram will have traveled 2 meters downwards, 4 kilograms will have traveled 2 meters upwards, and at that moment in time, each of those particles will be traveling at about 4.1 meters per second. Notice it's only an instant that they'll be traveling at that speed. So it's only for an instant that they'll be traveling at that speed, because they're accelerating all the time at the rate 3/7 g meters per second squared. Okay, so every second their velocity is increasing by 3/7 g meters per second. Okay, so that's the first thing. What happens? Let's look at another example. Same kind of system, but suppose I want to describe, suppose the 10 kilogram particle hits the ground after 2 meters. So maybe there's, you know, there's a bit of ground down here, and that's 2 meters above the ground, and this travels down and hits the ground. And I want to think about the motion of the 4 kilogram particle. Well, once that 10 kilogram particle hits the ground, it's no longer pulling down on the string. So once that hits the ground, all the tension will be gone out of the string. The string will become slack. The 4 kilogram particle would be moving upwards, but there's no force pulling it up. In fact, the only force acting on that after the 10 kilogram particle hits the ground, the only force acting on the 4 kilogram mass will be gravity. So once the particle hits the ground, all the tension is gone from the string, which means that the 4 kilogram is traveling vertically under gravity. In fact, the 4 kilogram essentially becomes a projectile at that moment. Okay, traveling vertically upwards under gravity. Okay, it's a projectile. It's traveling vertically upwards under gravity. Its initial speed in this phase, once the 10 kilogram particle hits the ground, the initial speed of the 4 kilogram particle, well, it'll be the final speed after this phase where it has traveled through 2 meters. We know when it has traveled through 2 meters, it's traveling at that value, 4.1 meters per second, or 2 root 105 over 5. Maybe we leave it in third form. So its initial speed would be 2 root 105 over 5. Its acceleration would be, well, if I'm saying this is a positive velocity, well, then the acceleration would be negative g. So the 4 kilogram particle just becomes something moving upwards with an acceleration downwards, and we can work out how long before it stops, reaches its highest point. We can work out how far it will travel upwards. We can work out all of that stuff as long as we know that at that moment the 10 kilogram hits the ground. That makes the string slack, so it becomes a kind of a slack thing as opposed to this taut thing. The 4 kilogram particle will go up under gravity though, and eventually slow down and stop, and then turn around and travel back down. And at some stage then the string will become taut again, and we have something called an impact or a collision, which again we haven't addressed that yet, but we'll talk about that in the next section of our course. So there's various phases of motion. So phase 1 is under the tension of the string. 10 kilogram moves downwards. Suppose it hits the ground then after 2 meters. Well, that introduces a new phase of motion where the 4 kilogram particle is traveling vertically upwards, but the only force at work on the 4 kilogram particle then, the only force at work would be the force on the particle by gravity. There's no tension pulling upwards. It travels up, it'll eventually slow down, stop, turn around, come back down, at some stage the string will become taut again, and we have a collision, and then it's traveling under tension again. So it's various phases of motion. Phase 1, traveling under tension. Phase 2, 4 kilogram vertical projectile. Phase 3, collision. Phase 4, traveling under tension again. So that's how it's going to work. Okay, so keep practicing those questions and see how you get on. Remember to let me know on Teams through the new conversation link if there's any problems.